Okay. So Dr. Tan, are you
Yes.
are you ready? Okay.
Yeah.
So I will make a quick introduction and then a quick announcement about the course. So we have a few students who enrolled in this course that after summer one, the score is not being put in because we will get the score after summer two. So that's not a problem. And then if you have any questions, you can let me know. Okay, so today it's a great pleasure to have Professor Ji Fu Tan from Department of Mechanical Engineering of Northern Illinois University. And his work is mainly on computational modeling, physics, and then high tech computation on complex fluids. So Dr. Tan has been simulate some of the blood cells moving in the blood that I have covered a little bit in my previous talk. So so let's welcome him, and then please use your reaction button to give him a very warm Texas style applaud.
Thank you very much for the introduction. It's my honor to be here to share some of the my research in the past few years with Texas Tech University. Actually, I was in Texas in 2009 for 1 year, and I have that's my first landing point in US. So it's a lot of great memories over there. I love Texas. So my name is Ji Fu Tan, an assistant professor in mechanical engineering in Northern Illinois University. Today, I'm going to talk about multiphysics modeling and parallel computing in complex fluid. To start with, I want to give a definition of complex fluid. Complex fluid is different from what we call the simple fluid, where usually it's called Newtonian fluid. You have one phase fluid, but for complex fluid, it's not necessarily one phase fluid. Instead, it contains multi-phases. For example, like the blood flow. The blood flow in small scale, you will see it consists of blood cells, cancer cells, platelets, and some even polymers or proteins. And at the same time, there are a lot of chemical reactions going on at the same time. So as you can see, to model such kind of problem is quite challenging. On the first on the title slides, I showed an example of cancer cells traveling through a microfluid device in blood cell suspensions. The red one are red blood cells, the green ones are the cancer cells, and those circular posts are microposts that are used to capture cancer cells in a microfluid device. So the outline of today's talk is the outline of the talk is as shown on the screen. First, I will start with the motivation why we want to study multiphysics problem in complex fluid. The next step would be how can we model such complicated problems? We will talk about what fluid solver we are using. How can we model those large deformations of blood cells or any other like deformable polymers? And then how do we couple those two different fluids and cells together, because it's a coupled problem. How can we handle the coupling between those two phases? And next, we will talk about how we can take advantage of the current modern computer hardware so that we can accelerate the simulation. That is what we call the parallel computing, or sometimes people call it high performance computing. And in the end, I will show you two examples for applications with such a powerful tool. One is in drug delivery, another one is in tumor cell detection, which is a collaboration with Dr. Lee from Texas Tech. So first, I'll talk about the motivation. Why am I interested in multiphysics in complex fluid? As you know that the leading cause of death in modern industrialized countries is cardiovascular disease, or you call it heart disease, and cancer, and stroke. If you combine all of them together, no matter for man or woman, about every 1 out of 2 deaths is caused by those two diseases. let's take a heart disease, for example. Heart disease basically is quite simple. It's just the blood vessel is blocked, so that there's no oxygen delivered to the cells. And because of unhealthy lifestyle or diet, a plaque, as shown on this figure on the right, the plaque grows so that it's going to push the endothelial cell, so that it's going to narrow the passage of the fluid in the blood vessel. And then once the blood vessel is narrowed, then the fluid is going to generate a huge shear stress. And that shear stress may rupture the integrity of the blood vessel wall, and then the tissue factor, protein, extra cellular matrix would be exposed to the blood, and then those platelets becomes activated, and then they stick to that injured area, and then it's going to platelets are going to release a lot of chemicals, going to attract more deposition of the platelets, and then as the platelets deposit over there, it's going to build up a clot. That clot is going to stop the blood flow even further, and then at one particular time, the whole blood vessel is blocked. So as you can tell from this example, it shows the fluid flow effect on the clot growth, as well as the red blood cell would be trapped over there. To model such kind of problem, we need a powerful tool that can model fluid flow, obviously, and then we also need to track the deformation of blood cells, as you can see on the middle figure. And those two are coupled together as well. So in order to model such kind of problem, we developed a high performance computational platform that is based on several different methods. The first one for the fluid, we use as you know that fluid can be described from different scales. From macro scale, you can use Navier, you can use the most celebrated Navier-Stokes equation as shown on the right. Basically, it says that equation on the right shows the acceleration, the force equals to the pressure gradient plus viscous force. On the other end, from a molecular dynamics point of view, you can solve a lot of like Newton's equations for individual atoms, and then collectively all those atoms can represent the fluid behavior. For Navier-Stokes equation, the solving technique, because you need to solve the matrix problem, it takes a lot of time. And from the molecular dynamics point of view, it's impractical to track a lot of particles at the same time. In particular, if we want to obtain some of the macroscopic properties, it's nowadays it's impossible. So what we choose here is a mesoscale approach called the Lattice-Boltzmann method. Instead of tracking individual atoms, we track the density distributions of those atoms, represented by F. And the governing equation of the Lattice-Boltzmann method is shown on the middle. Basically, it shows the density distributions change with time, and also traveled by the velocity difference in space. And then on the right-hand side, it shows a collision operator. That is, the density distribution functions is going to change after collision between each other. The reason we choose this is that Lattice-Boltzmann method is good for parallel computing. It can handle complex geometries, and also good for multi-phase flow. So to get a little bit further on Lattice-Boltzmann method, basically the variables now is density distribution functions F, not the traditional velocity, pressure in the Navier-Stokes equation. However, we can recover the velocity, the density, as well as the pressure based on that, the density distribution functions. The density distribution functions, you can think of as fictitious particles. Fictitious particles, they can, is kind of like a gas dynamics. They can collide with each other, and at the same time, they travel along in space. So usually Lattice-Boltzmann algorithm can be divided into two steps. First one is called collision. That is, they're going to change the value following certain collision rules. If you look at this figure at the bottom, initially we have some distribution functions, and then after collision, it's going to change its value, to a new set of values. And then after that, those distribution functions is going to stream based on the directions. They are going to jump to the nearby lattice. As you can see, for all those distribution functions at the center point, is going to jump to the nearby lattices. So at the northwest corner, jump to this point. And then similarly, for the nearby lattice distribution functions, you're going to jump to the center point. So this is called a streaming process. So this algorithm is quite simple compared with the Navier-Stokes, traditional Navier-Stokes solvers. That's why it gains its popularity. To couple the fluid flow with the solid cells in the fluid, we introduce another parameter. It's called force term F alpha over here. This F alpha depends on the external force, such as gravity or any force you applied to the fluid domain. And the collision operator omega alpha is replaced as a single relaxation time scheme. That is, we just introduce one more parameter, tau. Tau is a relaxation parameter. And then we use the difference between the distribution functions and the distribution functions at equilibrium, which is denoted by 0 at the top. And the equilibrium distributions can be expanded in terms of macroscopic variables such as the velocity and the molecular velocity direct vectors. And the viscosity is related to the parameter introduced in the tau. And see, in this equation, Cs is the speed of sound. For 2D lattice or 3D lattice, usually it's 1 over 3. And then the pressure can be directly calculated based on the density of the fluid. It's called the equation of state. And for a 2D lattice, we showed all the parameters such as the speed of the square of the speed of sound, the weight for each velocity vectors, as well as the velocity vectors along 8 or 9 different directions. That's it's a short introduction to the lattice Boltzmann method. Next, we're going to talk about the cell membrane model. Cell membrane model, we use a spring. It's kind of like a mesh. We use a spring connected beads model. That spring can bear stretching, so that when you pull a membrane, the spring can resist pulling. And then at the same time, we consider the bending resistance from the lipid bilayer. So we have a bending potential applied to the membrane. And because during the deformation, the cell membrane as well as the cytoplasm is relatively incompressible, so we added another 2 extra potentials related to the total surface area of the membrane as well as the volume of the membrane. So obviously the simplest spring we can use is a harmonic spring, right? F equals to Kx. But here we use a slightly complicated one. It's called the worm-like chain model to better characterize the membrane stretching behavior. But the idea is the same. It's just a spring potential. And then for the bending, that is the bending stiffness coming from the nearby membrane. Nearby patch of the membrane, we apply a cosine angle dependent potential so that the membrane can retain its equilibrium shape. And then for the area and the volume potential, it's just a harmonic potential based on the local area and the total surface area, as well as the volume of the cell formed by the surface mesh. As it can be shown that this kind of approach can be related to continuum model, such as based on the shear modulus measured from experiment data, we can determine what's the correct spring constant we should use for the cell membrane, as well as the bending stiffness we should use for the 2 triangles formed in our model. Besides Laplace cells, we also consider the polymer chain model to model like a nanoworm particle or like any protein in the blood stream. So essentially the same thing. We use the same worm-like chain potential to represent the stretching, and then we apply a harmonic angle-dependent potential to model the bending stiffness formed between 3Ds or like between two bonds. And then to avoid the overlapping or penetration between the particles, the cell, or even consider the adhesion between the cell and the surface, we introduce a Morse potential. Basically, it's kind of like it's kind of a harmonic potential we use to represent the interaction between the adhesion between ligands and the receptors, or when those two particles come too close, we want to avoid the penetration. We apply a repulsive force based on Morse potential. Those are the solid models we introduced. The next question we want to ask is, how can we couple the fluid flow, which is solved by the lattice-Boltzmann method, with the solid motion provided by the cell membrane model? Traditionally, this kind of approach is based on arbitrary Lagrangian or Eulerian method. That is, we use one set of mesh, one for the fluid, another one.
Pan?
Yes.
May I ask a question?
Yes.
So can you show your previous slides?
Yes.
Yes. So I have so you have here particle cell interaction, and then
right.
So the red one are the red blood cells, and the green one, I believe, is the platelets. Is that?
The green one is a polymer. Are you talking about the top or the bottom?
Okay. So the green, the top one is the particle.
Right, like a polymer. The
like
bottom one is a platelets.
Polymer solution, right?
Right.
Okay, and then the second one is the platelets and the cell interaction.
Right.
So those ones, did you think they are, if the plane is attached to the surface of the cell, is this going to change your, like the spring constant and all those things in your model?
So right now, ideally we should, because platelets is kind of an active cells, right? Platelets can solidify itself, can strengthen the bonds they formed between its receptors and the receptors expressed on the cells. In our model, no, we didn't consider that. I mean, when they bonded together, the spring constant is still the same, but we can change that if, like, say, we define a status variable to track the activation status of the platelets. Once the platelet then is activated, then we change it to a new set of parameters. It's doable, but in the current model, no, we didn't implement that.
Okay, sure, thank you. Yeah.
Okay, thank you for the question. The next part is we want to couple the solid motion with the fluid. So as usually in the literature, what they did is they use the same mesh for the fluid and the solid, so that the fluid and solid share the surface nodes. This approach is great because it's easy to apply boundary conditions. For example, the non-slip boundary conditions between the fluid and the solid, right? But there's a problem for such kind of approach. If you look at this example at the, look at this figure at the bottom, I have a red square block is rotating because the mesh, the surface nodes is shared between the solid, which is indicated by that dark area, and the fluid, which is the surrounding fluid nodes. Then the mesh, once the block is rotating, the mesh is distorted. And then if this rotates several rounds, what's going to happen? Then all the mesh are entangled together. That's going to significantly deteriorate the calculation results. So one solution they propose is we have to remesh. I mean, during each deformation, we have to regenerate the mesh. That's tedious, and also it's time consuming as well. So that's why this approach is good for simulating small deformations. Like the deformation is relatively small, it doesn't distort that mesh that much, as shown on the top figure. It's deformed slightly. However, for our case, like the rubber cells, they deform significantly, as you can see from the later simulation results. If we want to stick to that approach, it's impractical. It's going to spend a lot of time remeshing, generate a new mesh for after each time step. So what we used here is a method called immerse boundary method. we use two sets of meshes instead of one, so that those two meshes doesn't share any surface node at all. They are independent with each other, one for the fluid, one for the solid. And then let's come to the problem. How could we apply the boundary conditions correctly? Then we use the two steps. One is called the velocity interpolation, so that we assign the local average fluid velocity to the solid surface nodes, so that the non-slip boundary conditions can be applied. And then at the same time, we make sure the force, the stress on the surface membrane is transferred to the fluid as well. Which is represented by the second equation. We spread out the solid force to the local fluid. We use the delta function, that is an interpolation function, to find the average of the fluid and also spread out the force to the local fluid. As you can see from the figure on the left, from the fluid velocity, we have ux, and then we have the solid velocity, capital U, capital X. And then in order to calculate the capital Ux, we do an average for the surrounding fluid. And then apply that average velocity to the solid. Similarly, for the force, we calculate the solid force, and then that solid force, F capital X, will be distributed to the local fluid, so that the fluid can feel the existence of the solid. In this way, we achieve the two-way coupling between the fluid and solid. And then you can choose different versions of delta functions. You can use 2 nodes or 4 nodes. Usually, the higher number of nodes you use, the more accurate it will be. But again, at the same time, it costs more because you have to do more calculations for the surrounding fluid nodes. That's the idea of the immersed boundary method. And then I quickly go through the coupling algorithm. Basically, starting from time step T, we have the cell position as well as the local fluid velocity. And then from the cell configuration at capital X, we can calculate what the deformation force is based on the potential defined previously. And then we calculate the solid force. The solid force can be spread out based on the spreading algorithm, spread out to the fluid. Then through that immersed boundary through spreading algorithm, we get the fluid density force, that F. That F will be incorporated into the Lattice-Boltzmann method, so that the body force can drive the fluid flow. And then we update the fluid flow velocity to the next time step. And then from the fluid velocity at the next time step, we do this kind of velocity average or velocity interpolation. We get the solid velocity at the next time step. And then from the solid velocity at next time step, we can update the solid position to the next. Then we completed the one cycle of the time stepping. So to test our model, we compared our numerical results for the cell stretching with the optical tweezer experiments. Basically, what optical tweezer experiment did is they apply optical tweezer to stretch the red blood cells and to measure the longitudinal diameter and the transverse diameter. Longitudinal diameter is plotted in the top curve, and the transverse diameter is plotted at the bottom curve. As you can tell, at the different pair of forces, then if you increase the pulling force, the longitudinal diameter will become bigger, and then the transverse will become smaller. And the data with the error bar shows the optical tweezer experiment. And we did exactly the same thing in our numerical model, apply the same amount of force to pull the red blood cells. And then we plot our data in these solid lines. As you can tell, our model can capture the optical tweezer behavior, the cell membrane stretching behavior quite well. So we can say that we have a highly accurate red blood cell model for the biological flow studies. The second one we did is we want to validate the coupling, because previously we only validated the cell model. What about the coupling? How do we know the coupling is correct? So we compared our numerical simulation with an analytical solution proposed by Jeffrey. It's called the Jeffrey's orbit. What Jeffrey orbit experiment is, we have an ellipsoid particle in shear flow, and then the rotation of that ellipsoidal particles follows this kind of equation, depends on the shear rate, depends on the major axis, the length of the major axis and the minor axis, as well as the time when you simulate that. We compare our simulation with the theory plotted in the top figure. As you can tell, they agreed pretty well, and the relative error is quite small as well. And we also check the convergence of this method. It shows that as we increase the number of the fluid nodes, the error reduced. The error is in the first order because it's an explicit coupling between the fluid and the solid. And then we studied the effective viscosity of blood in blood cells in tubes with different diameters. And then the curve shows the experiment data where they made a lot of blood viscosity on the different sides of the tubes. They get this experiment fitted curve. And then our simulation data is shown as the red data point. And we also compare our numerical simulation results with the boundary integral method, which is shown on the green results, green points. As you can see, our approach can also capture the effective behavior of red blood cells in blood flow as well. And the bottom figure shows the self-deformation on the different on the tubes with different diameters, 5 micron, 6 micron, 8 micron, until 30 micron. So as you can tell, from this kind of simulation, it's quite expensive because you have to resolve the deformation of the cell membrane. This is kind of difficult if we only use one processor or one computer to do that. So nowadays, we want to take advantage of the modern processor hardware, such that everybody knows that we have, even the cell phone has multi-core processors. So how can we use that? So let's come to the third topic. How could we implement a high performance computing software or code that can be used to attack more sophisticated biological flow problems? So before I was started, I have a few questions. First one, we have to realize that it's an expensive calculation. It needs to crunch the numbers many times. And then should we start from scratch? It looks like if you start from scratch, everything is under your control. But at the same time, it may take you forever to develop such a powerful tool. So the approach we took is we don't want to reinvent the wheels. We want to make use of existing open source code. There are many high quality open source codes. We pick up Palables and LAMMPS. Palables is for the fluid. LAMMPS is a molecular dynamic simulation for the solid. And also we believe that we make the simulation software to be open sourced so that everybody can have access that it's going to, we believe open source code is going to encourage the replication of others' work and to incorporate the collaboration from different groups as well. So
Dr. Tan,
yes.
May I ask a question here?
Sure.
So can you go back to your slides? Yes. So some of I think a lot of my our students is not like their research area is very diverse. So
right.
Some of them are working in the computational, but a lot of them are working in the experimental. So couple of like kind of introduction question here. In the high performance computing area or field, what
right.
exactly the expensive means or cheap means?
Okay.
Time.
Yes, time, like memory resources, like computational power. Think about it like, say, if you want to run like this kind of simulation on a desktop computer, it may take, I don't know, I never run it, maybe take 1 month or something. But if you run it with a computer with multiple processors, or even in computer clusters, you may get it done in 1 day. And also, if you know, the memory, usually for one computer desktop, probably you have 16 gigabytes. But if you have access to a high performance computers, you have like a huge amount of memory. Memory is not an issue. So that's what I mean by expensive. You have to put a lot of resources over there. One laptop is not enough. One desktop is not enough. You have to use a computer clusters. That's what I mean by expensive. That means you have to, it demands more resources, either memory or hard drive or computational power, those kind of things?
Yes. So let's say when we do experiment, we like to say, okay, we've spent a few thousand on materials. Like one antibody can be a couple of milligrams, and that takes a couple thousand. And some of those can be micrograms, and then a couple hundred. So we have some scale with respect to how to quantify expensiveness. But in the computational world, let's say run your like a program that you have here, like time, and also if you use the computational clusters that I think that are shared by the university, right? Or some even multiple universities that high performance computational center. What are the costs? Like say what are the dollars for per hour or something?
Okay, that's a good question. It depends. When I was at Lehigh University, they charged based on semesters. I think it's about $450 based on how many CPU hours. So it's allocated based on CPU hours. Like say you have let's say you have 10,000 CPU hours. That means you can either run like 10,000 CPUs, and then you can only run 1 hour, because multiply them together, you get 10,000 CPU hours. If you use 10 CPUs, then you have 1,000 hours. So that's what I had at Lehigh. And at NIU, it looks like they are pretty generous. It's pretty much free. So as long as, I think that's good about NIU. Like if you do computation, you pretty much get all the free computational resources. So it depends. I think it depends on the school policy. Some school would charge based on, if you are a faculty, probably you will get some discount. Another mode I am aware of is that they would sometimes, as a faculty, you can contribute some of the computational resources. For example, you can help the computational center to buy some computers, or like I buy 100 processors, I put it over there. You help me to maintain it, and then I can, that's my grant money or my startup money, and then they may charge less or they may not charge you. So there are different modes how to get access to those things.
Okay, good. So thank you. And there's another question from audience. So we have Dr. Jay Nu. He's our new faculty will join in the fall. So he has a quick question saying, how do we determine whether a problem can be potentially suitable for parallel computing, or you just need a desktop?
Okay, that's a good question. So one thing you can do is you can do a quick test, right? If you do computational modeling, like say, based on what kind of scale you are modeling, I could do a quick test. For example, I can run it on a desktop computer. How long does it take? If it takes like 1 month, probably I would say, no, that's too much, right? Then next, you may want to consider to move to a high performance computing. And then for that scenario, you have to consider for your problem, is there any good algorithm that can partition the problem so that you can divide that whole task into individual ones, so that each computer can run individually. Some of them, for example, if you run Monte Carlo simulation, you just have a different trials, and those trials are completely independent. That's great for parallel computing, because you don't have to worry about the dependence between different processors. However, for some problems, it's kind of sequential. There's no way you can run in parallel. For example, for this kind of talk, I cannot run in parallel because I have to go through the first part and then the next one. There's no way you can divide me into several parts. So it's problem dependent. And for our problem, like say, I will talk about that a little bit later, how I divide the simulation task into a small domains so that each processor can run independently. I will talk about that in the next section. So to summarize, it's problem dependent. To know if your problem is suitable for parallel computing or not, I would suggest you try your problem with a single computer first to see if the performance, the computational time is satisfactory or not. If you are not happy, then you can consider to move to high performance one. And you can check some literature or other work to see if there's any similar work that has been performed in high performance computing.
Okay.
I'm not sure if I answer your question or not.
Jay, is that answer your question?
Yes, thank you.
Okay, thank you. I will talk about that the details how we can break a complex problem into small problems so that each small scale problem can run on a processor. Okay. So going back, so we want to take advantage of high performance computing. We want to take advantage of the open source ones as well. So what we did is we use Palabos. Palabos is the open source. It's pretty good. It's relatively easy to use. It can be used to model complicated fluid flows, such as like the turbulence in a washing machine, the droplet formation in a T microfluid T channel, and then simulate the biological flows in a stand and compared with commercial software CFX, which is part of the ANSYS company, I believe. And then for the solid solver, we choose LAMMPS. And then LAMMPS, again, is quite popular. It's very famous in molecular dynamics simulation field. And now comes to the problem. How can we take advantage of parallel computing? Let's say this is the flow system with particles we already have, right? We simulate the blood flow in a microfluid channel. This is the whole simulation domain. I want to take advantage of parallel computing. What we did is we use a geometry-based decomposition technique. That is, the whole simulation domain is divided into small chunks. Here shows an example. The whole simulation is divided into 16 small domains, 1, 2, 3, 4, and then the top 8 at the top and the 8 at the bottom. So I did exactly the same partition for the fluid and the solid. So that the fluid, one processor handle the calculation in that small domain. Similarly, the same processor will handle the solid calculation, the cell deformation as well, right? And then in such scenario, the same processor can have access to both the fluid and the solid because they are coupled. So I need access to both of them. Because even we can use existing software, we still have to build the interface between the Palabos and the LAMMPS because they are two completely independent software. They don't necessarily talk to each other. And then it's your responsibility to make sure those two software talk to each other. That's what I contributed over here. I wrote the interface code so that those two software can talk to each other in memory, so that I can have access to the particle position, the fluid velocity, the force at the same time. So I can do some manipulation of them. It turns out that through this experiment, hundreds of lines of interface code, we can get all the capabilities of both Palabos and LAMMPS. That's amazing because think about it. If you want to start from scratch, I don't think I can complete it in a few years. Maybe in my whole life, I probably couldn't complete all of them because nowadays software engineering requires a dedicated team with people from different backgrounds, from computer science, from engineering, and even they have to spend like tens of years working on that software. So there's no point to starting from scratch. So it turns out this approach is quite successful. We run it a relatively large scale simulation with 15,000 of cells, and then run it on Argonne National Lab supercomputers. So we checked how many times the simulation could be speeded up if I run with multiple processors. We choose the 512 processors as the starting point, and then we just every time we just double the number of processors. We dump more processors to see how fast I can get. So ideally, the speed up should be linearly, right? Think about a task. If I do it myself, it takes me 1 week. If I ask 2 people work on the same time, probably we can complete it in half a week. But in simulation, because that's an ideal case, in reality, it doesn't work like that because you need to schedule a meeting. You need to talk to each other. The same thing applies to computers. Computers need to talk to each other, need to communicate with each other. That would take some actual overhead in terms of communication. So, so ideally it should be linear, but we didn't achieve a perfect linear, but still the performance is quite good. And here I shows two different cases. One is called a strong scaling, and another is called a weak scaling. For strong scaling, basically means the total amount of work is fixed, and then I just need to put a lot of processors. For weak scaling, basically it means for each processor, the work is fixed. If I double the processor, I double the total amount of work as well. So those are two different mechanisms to measure the performance of any high performance computing code. So this the table also shows how much time is spent on for the inverse boundary algorithm, how much time is spent on the interpolation, how much time is spent on the spreading forth. It takes about it depends on how many processors that you have used. I only tested on 16 processor. It's about 25 to 30%. That's the communication between two different softwares.
So
I think I saw.
have a question.
Yes.
Carl. What?
Yeah. Oh, I had a question. Yeah, you said that you use Palabos lamps in your interface code that you wrote. I'm wondering, you had a few more on the previous slide,
Right.
OpenFOAM, FEN, ICS, etc. I'm wondering, why do you need those two?
Okay, so the reason is that Lattice-Boltzmann method is crazy for parallel computing, because the reason is like this. There's no way, you don't need to solve a matrix problem. If you use OpenFOAM or even Phoenix or even what's that called? DO2 or even there are a lot of finite element based on finite element, finite difference, or even finite volume method. Eventually, you get a big matrix, right? You have all those unknowns. You have to solve all those unknowns. You have to solve a big matrix problems. Even you can use different preconditionals, very fast linear solvers, but still you have to solve that linear matrix problem. But for parables, there's no matrix at all. You just need to run the density distribution functions, and then it's jumping around. There's no calculation in terms of calculate the inverse of the matrix to get the solution. So in that sense, it's quite faster. Actually, in one of the class, I asked the student to compare the difference between finite difference method as well as a Lattice-Boltzmann method. Lattice-Boltzmann method is way faster. That's why we didn't choose OpenFOAM or Phoenix, because for those methods, you still need to solve the linear.
Oh, you didn't choose those?
No.
Oh, okay.
Because that one is it's slower.
Right.
And then if we want to run large scale, I just want the faster the better, right? And then what's good about this, nowadays people can use a GPU to run in the Lattice-Boltzmann method. Because think about it, if any small scale research group, right? I may not have access to those large scale computers. It's also quite expensive as well, right? Not everybody have access to Argonne National Lab, or if I'm not lucky, my school doesn't have any high performance clusters, then I'm dead. Now, in the Lattice-Boltzmann fluid solver, they have one called Warbler. It's a German open source software. They can run it in GPUs, and GPUs compared with CPUs is relatively cheap, like $10,000. You can get a pretty good GPUs, and then the GPU also runs much faster. So that's why there's a whole momentum try to push the safety field to those, to accelerate the safety with modern accelerators. That's the reason I choose Palabos. And for the solid, again, I choose the Palabos because for the solid I choose the lamps because it fits naturally with because I use the springs, a lot of springs connected back together to form the cell membrane. So it naturally fits the design of the lamps. And I can also use polymer models, a lot of predefined potentials by lamps. And what's furthermore, lamps also provide those thermal fluctuations. Like depends on, again, that depends on the scale you're looking at. If you just look at a macro scale, probably you don't need to worry about the thermal fluctuations. But if you look at a small scale, like particle transport, then you do. So that's why, I mean, I choose lamps.
Okay, yeah, thank you.
Okay. So, okay. So I have showed all those methods in terms of developing such a powerful computational platform. And then I want to show you two applications. The first one is called drug delivery. Previously, we showed that through the design of the drug carrier, for example, the size or the shape, we can achieve different adhesion probability when those drug carriers stick to the vascular network surface. And then it's all that adhesion distribution also depends on the geometry of blood vessel shapes. And then we also compared our numerical simulation for this particle distribution in blood cell suspensions with the experiment data. As you can tell, when mixed red blood cells with nanoparticles, 100 nanoparticles, we see more particles close to the edge of the channel. Compared to the case without red blood cells, the distribution is more or less kind of uniform. The same trend is also observed based on microfluid experiments. Look at by checking the fluorescent intensity of the particles across the channel. So we can see that red blood cells can somehow influence the particle distribution, so that the more particles toward the edge of the blood vessel. And we also look at the motion of the cells under the different shear rate. Is the video playing?
No, video is not playing.
It was
Okay.
playing like before.
Yeah, it looks like it's playing and then all of a sudden it's stopped.
Maybe you should, can you, maybe you have, it's better to like close it and then open it again, or?
No, let me go back. Is it playing now? Looks like it is, right?
Yeah, now.
Okay, so
yeah, playing, yes.
This one shows the red blood cell motion in different shear rates. The top at the high shear rate and the bottom as the relatively low shear rate, 100 reciprocal second. As you can see, the red blood cells showed two distinct behavior. At the top, the cells more or less kind of align with inclined angle. But at the bottom, you will see the cells is going to rotating like a coin. So that's what we call tinctretic motion and the tumbling motion. And on such a flow cases, we also see a cell-free layer, which is well observed in literature. That is close to the blood vessel wall. There's no cells because the cells is deformed. They tend to migrate toward the core, the center of the blood vessel. We also check the stiffness and the size of microfilaments in blood flow, because one paper they mentioned that they observed a long circulation time for worm-like particles in rabbit model. So we want to see why that's like the case. So we performed the simulation of a mixture of both particles and the cell suspensions. We also changed the stiffness of the particles. One is more flexible, and another one is relatively rigid. So we check the fraction of the particles along the radial direction. So as you can tell, for small particles, 2 micron length, the soft particles and the stiff particles looks like they are more or less kind of similar because it's quite small, it's not sensitive to the stiffness. However, if we look at 8 micron particles, because the cell size is also 8 micron, and the soft particles can relatively traverse through the cell, the gap formed between the cells relatively easily. But for the rigid ones, it's difficult. But once they get out of the central region of the cell, it will stay in the cell-free layer region. We also characterize the dispersion rate based on mean square displacement for the particles with a different size and a different stiffness. And it shows that the dispersion rate is much higher than thermal fluctuation rate. or the diffusion rate induced by thermal fluctuation. That means the red blood cells can enhance the the particle dispersion rate in blood flows. So a quick summary, we showed that particle transport, we started the particle transport with different size and different stiffness. Mixing with red blood cells, particles showed enhanced the dispersion rate, which is much higher than thermal diffusion coefficient. And the softer particles can traverse cell layers relatively easily compared to our rigid ones. And next, we'll talk about another application.
We have another question from the students.
Sure.
Pankaj, you'd like to ask a question?
Yes. So Palabos, since he used, which is for Lattice-Boltzmann method, so it's based on C++, and then LAMMPS package is also based on C++, right?
Right.
So if you you can include header files from LAMMPS in C++ code, right? But if you're writing a code in Python, like if I'm using NumPy library, how can I include header files from LAMMPS? Like if I have to use if I was to use both fluid and solid, as in your case for micropost and the cancer cell.
Okay, so you are using Python NumPy library, right?
Yes.
Okay, I never tried myself. I believe Palabos, they provide a Python interface, and I believe LAMMPS also provide a Python interface so that you can call those libraries directly from Python. But I never tried myself because I just directly write the code in C++. I didn't use this kind of like a wrapper package with Python. Python is great for wrapping language that can call different libraries, but personally, I never have experience with that.
And how about the computational speed? I mean, so is it comparable, or is there's a big compromise of like if I move to Python, or because C++ is pretty much faster, but using NumPy library, it gives comparative speed, I believe.
Okay, I never tried it myself. I couldn't, when we talk about performance, I would prefer like side-by-side comparison. I didn't do it myself, so I couldn't comment on NumPy versus C++.
Okay.
But okay, but what I know is that if you use Python, just pure Python, it's much slower. NumPy, I'm not sure, so I couldn't comment on that.
Sure. Thank you.
Okay, thank you. And the next application is about tumor cell detection in a microfluidic device. Recently, it has been shown that a microfluidic device can be used to detect earlier circulating tumor cells. Different designs have been proposed, such as circular post or triangles, or even displacement lateral devices. Then the question we want to ask is, if we flush the blood sample with cancer cells through such kind of device, where would the cells be captured? What's the effect of the ligand density, like the coating density we had on the micropost surface, poster size, and even the design on cell capture? How does the cell collision influence the cell capture? Is it going to enhance the cell capture, or is it going to reduce the cell capture? How do we determine the capture efficiency based on the design patterns? Actually, this is a collaboration with Dr. Lee from Texas Tech. So his group provide the microfluid device design, and our group perform the numerical simulation. We have two different designs. One is called a regular design, another one I call the shifted design, as shown on the figure. And then we set up the simulation based on using the following parameters. For those details, if you are curious about all those details, you can find in the by our microfluid device paper. So first thing, we started the cell rolling and adhesion on a single micropost. We want to see how does the cell interact with the coated surface on our micropost. First, we check the cell adhesion on the different ligand density. The reason we select the different ligand density is that it has been shown that the most active cancer cells has expressed a lot of receptors compared with the relatively less invasive cancer cells. So we showed that with the higher density of ligand, the cell stick firmly to the micropost surface. If there's a less ligand density, the cells tend to sleep on the touch the micropost surface quickly instead of form a firm adhesion on the surface. We also check the cell sizes. We check the size with 8 micron diameter, 12 micron diameter, and 16 micron diameter for cancer cells. We show that the adhesive force is time dependent. As you can see on the middle figure at the bottom, the cells, the adhesive force reaches to its maximum before it reaches to the crest of the micropost. And then once it's rolled over, the adhesive force decreases as well. We showed that the adhesive force is strongly depends on the contact area, adhesive contact area, and the cell size, the cell diameters. And it shows, it looks like it follows second order. It's a relation of it's a quadratic function of the cell diameter, because when you have a larger cell diameter, the contact surface is relatively larger as well. We also, the top figure shows the adhesion of one particular cell on a micropost in the microfluid experiment shown on the left. And also we captured the same adhesive behavior for the cell on the, in the simulation. At the bottom shows the preferred adhesion of cells on the micropost surface. As you can tell, the most of cells tend to stick to the low shear region, either in the front of the micropost or at the rear end of the micropost. The same behavior is also confirmed by the microfluid experiment as shown on the right. White two figures, the green one is the cancer cells or cancer cell clusters. And then the next shows a few simulation movies as well as microfluid experiment movies. You show the light green ones traverse from the left to the right. Those are like cancer cells or cancer cell clusters. And then the top figure shows only the cancer cells transported in the microfluid device. And the bottom two shows the transport, the mixture of cancer cells and the red blood cells. The left shows a 4.5 volume percentage of red blood cells, and the right-hand side shows the 10% red blood cell concentration. The first thing we checked is the cell trajectory in simulation and experiments. The top figure on the right shows the cell trajectory in the microfluid device experiment. It's showed in different markers, and the blue line shows the simulation, shows the trajectory from the simulation. At the bottom shows the trajectory from the simulation for the cells, as well as the streamline. Because one thing come to, when we look at the trajectory of the cells, one thing come to our mind immediately is that they resemble the streamlines. So we want to compare the streamline and the cell trajectory. It looks like most of the cells follow streamline, but that's not for all the cells. Here we show the four particular example where the cell trajectory is changed because of the collision, because of the intercollision between cells. As you can see, the red line shows the streamlines, where at each point the tangent direction indicates the flow velocity, and then dark line shows the actual trajectory of the cells in the simulation. As you can tell, if there's no cell collision, then the cell would follow the streamline. But because of the collision between the cells, the trajectory is completely changed. In particular, if you look at B or D, the trajectory is changed significantly because of the collision at that particular point. So to quantify the difference between the actual cell trajectory and the streamline, we define a parameter called EL2, the distance L2 norm. If this idea is borrowed from finite element method, it's similar, like kind of like an arrow L2 norm. So we integrated the error, the difference between the cell trajectory and the streamline, and do the square and integrate it over time and divide it by time as well, and then take the square root. It turns out that for smaller micropost, the average displacement between the streamline and the cell trajectory is about 32 micron and plus or minus 9.3. And then if we increase the micropost from 45 to 50 to 55, the cell shifted distance is also increased from 32 to 36 micron to 41 micron. And then we pick up one particular design with the micropost of 50 micron. We compare the difference between pure cancer cells with 5% of red blood cell concentration, and the case with 10% of red blood cell concentration. As we can tell that when we increase the number of red blood cells, the shifted distance is also increased as well. That means the mixture of red blood cells is going to enhance the collision or enhance the dispersion of the cancer cells in the microfluidic device. That is going to increase the collision chance between cancer cells and the micropost. Next, we do the statistical analysis of the cell adhesion location on the micropost. The left shows the adhesion location on the micropost in a simulation, and the right shows, at the bottom shows the adhered cancer cells on the micropost. And then we also compare the adhesion for different micropost sizes on the top. And then we measure the angle. We characterize the location based on an angular parameter called theta, measured from the horizontal angle and go all the way to all the way around. So if theta equals to 0, which means it's adhered to the rear end of the micropost. If theta equals to pi, which means it's to the front end of the micropost, because the flow moves from the left to the right. And then the figure D shows the adhered cells on the micropost in a microfluidic device experiment. As the frequency data is also shown in this figure. As you can tell, most of the cells tend to stick to either in the pi, in the rear, in the front end, or at the 2 pi, close to pi, which is the rear end of that micropost. It shows that the cell tend to stick to the low shear region, which is what we expect based on the previous simulation results. So to summarize, we showed that the cells prefer adhesion in the low shear stress region, and the cell rolling and adhesion in micropost on the different cell size and ligand density showed a time-dependent adhesion dynamics. The trajectory, the cancer cell trajectory deviates from the streamline. The difference increases with post size and the cell concentration. For the future work, we would like to study the cancer cell capture at high shear rate, as well as the different design to optimize the microfluid capture efficiency. So in the end, I would acknowledge my group at NIU and also my advisors from UPenn and Lehigh. And I would like to thank the NIU Gaia High Performance Computer Facilities and Argonne National Lab MIA supercomputers, so that we can validate the performance of our simulation framework. And thank you very much.
Thank you very much for the talk. And now the floor is open for questions. We have a question from Pankaj. Pankaj, you want to ask questions?
Yes. So these microposts in this geometry were used to capture these cancer cells via adhesion, right? So how much was the cell capture efficiency? I mean, for these geometries you have used, like for example, how many cells were successfully captured via adhesion?
Okay, I think that's a good question. There's a there's a difficulty in evaluating the capture efficiency in such a small device, because if you look at the actual device, I remember from the experiments test, they can capture the cancer cell capture efficiency about 90%. But for our case, because we only have a relatively small domain compared with the actual microfluid device, which is about the 3 centimeter, right? And in our case, we only simulate about 500 micron. Then it's kind of hard to evaluate what's the, how make a side-by-side comparison between the
Experiments.
That's right. And also previously I had a section for that, but I removed it this time because previously we showed that if we only look at the capture efficiency with a single unit of that microfluid device, based on that, just give me a second. Let me find that. I can.
Okay, I'd like to jump in just when you find the file. Just jump in to answer some of the experimental part. So Pankaj, for those devices that capture efficiency, if it's for experimentally for the post device, it will go up to can go to 60 to 70% if you use a cell line as your spike in there. You know the total number, and then you can count how many cells are being captured on the cells and on a chip. Then you can do a calculation, and then but that also depending on a couple of factors. One, as Dr. Tan said, the area of the chip, right? The bigger the chip, the probably you will have a slightly better capture efficiency. And also, depending on the flow rate, lower flow rate might be slightly better, but lower flow rate can create some clogging problems if you have red blood cells in there. So some of the the modified device can get the capture efficiency up to 80 to 90%, and then. We also had another work previously by my group. They put nano particle on the surface of the micropost, so that will enhance the capture efficiency to up to 95%.
Nice. And the collisions, between the cells, that will affect. So if we increase the flow rate, so the probability will will be very different as we have low flow rate. The collisions will be less for the low flow rate, I assume. And I mean, so even if my cell is colliding to the micropost, I mean, how much probability is that it will be captured, or like it will stay there, or it will get detached from the micropost as as my flow is going on, and more cells are coming to the micropost.
So Dr. Tan, is that?
Yes. Can you see? Okay, can you see my new slides?
Yes.
Okay, I think this one shows the capture efficiency. Basically, we define capture efficiency as the ratio of how many of the cancer cells captured and the total cancer cell released. So for the radius of 45, 50, 55 micron, we showed the capture efficiency for 6.5%, 8%, and 15 and 16%. So because this is the capture efficiency in such a small unit, right? Just represented by the one of the red rectangular domain. So, and then in order to compare with the big scale, like say the actual microfluid device, it's about 3 micron. 3 centimeter. So what we did is we assume the whole device can be represented as a sequential array of individual units. So the cancer cells exiting from one unit would come back and enter to the second unit, right? So we can combine all of them together. We assume that follows a simple geometric sequence. And then if we follow this assumption, we can calculate what's the capture efficiency. For example, if we choose the 50 micron as an example, 50 micron device, micropost device as an example, we put it over, it's about 97%. And then from the experiment results, it looks like it's around 90%. And then because this is obviously is an ideal, because we assume all the cells or all the cell, the capture efficiency would be exactly the same after each unit. But in actual case, it isn't, because once the cell captured in the previous unit, then the number of cells would be less in the subsequent units.
Mm-hmm.
But
Yes.
however, in my assumption, I just assume, okay, the capture efficiency is the same for each single unit, so that I can use this geometric sequence. You're right. I mean, it's hard to make a direct comparison, but we tried our efforts. And there are some critics like say this kind of assumption is not that valid, but unless we can simulate the capture efficiency in the whole mega scale, megafluid device scale.
Yes.
Otherwise, I think I can only report this is the capture efficiency in the single units is 6%, 8%, and 16%. And then how could we extrapolate that capture efficiency to the actual whole device? I think that requires more research.
Yeah. Thank you for answering the question.
Thank you.
Okay. Any other questions? Okay. If not, let's give Dr. Tan a round of applause using your reaction button, and then I will see you next Tuesday. Thank you, Dr. Tan, again.
Thank you very much. It's my honor to share my work over here. Thank you.